Okay, good morning, guys. Hopefully everyone can hear me, and also I hope the audio quality gonna be a little bit better than yesterday. So hopefully I'm not gonna have fan noise in the background. As far as my computer fan is concerned, AC fan, yeah, it's probably gonna kick in every now and then. Also, my dog might bark every now and then, just to annoy us. Okay, so we'll see if anybody else gonna show up, or it's only gonna be 6 of you, 7 of you. So we'll see how that works, or if this is useful for you guys. The recordings of these sessions are linked under the archive, and you guys can look up previous recordings if you missed some of them. And after this week, we'll see if you guys need this, or you guys can just go through the chapters on your own, and we can just discuss some concepts on discussion board. And some of you already started that kind of a discussion, so that's good. Seems like you guys feel comfortable with this whole concept of online courses, that you guys can really help each other out. Okay, so let's get started with this. We're going to be talking about basic concepts. Okay, so we're going to be reviewing what you have to know, or what you should know at this time about Java. And then we're looking at Chapter 1, concepts. And I'm going to pull out information that might be very relevant, or the most important concepts in this chapter. But the book is really good. If you read the book and you do all the exercises, I think you're going to find that the book author gives a really good explanation for all the concepts that we have to know in this particular course. Okay, so hopefully you guys have a basic idea why we are looking into data structures, or this particular course. So many people that learned programming on their own, or watch a lot of YouTube videos, you see that those videos and many concepts in programming are focusing on syntax and solving some problems. In this particular case, in this particular course, what we are really focusing on is how do we solve those problems. So it is not really just the coding that we need to focus on, but is the code efficient enough to handle a problem, especially when the problem grows to a larger size. And that's what we need to focus on. So we need to look at how long a program takes. And another concept that we have a problem with in most of these courses is looking at flow charting and looking at pseudocode, which is basically designing the code. Because so far, most of you have written small programs, or programs that only considered a small data set. And most of those programs you can write without analysis, without any kind of a design, because after learning, after going through basic syntax problems, and you understand a language, then with small problems you can see the solution. Now that's not going to work when it's about data structures. Okay, the easiest way in designing something is to write the pseudocode and then analyze the pseudocode for speed estimates. And at the pseudocode, the design aspects, when we're thinking about design, that's when you have to fix design flaws, or replace some of the algorithms for something that's going to be suitable for that particular application. So we need to know what the application is for. When you are, let's say, querying a application for the cheapest airline fares, you are not changing anything in that database. You are just reading it. So what you want to optimize your code for is the fetching, is the reading of the values. Right? So you need to look at what is the application for, implement or design an algorithm around it, and then see if it's going to be sufficient for that particular application. And later on, if the application changes, you might also have to replace certain parts of it. So flowcharting and basically designing is going to be very crucial aspects of this concept of data structure and program designs. Okay, so let me share my desktop, and also give me some feedback if there is better response time from the system today. Okay, so you should be able to see my desktop. Okay, so first of all, one thing you have to do is hopefully you picked your IDE, right? And then under the syllabus, you go to the link for the book author, the publisher's website, and under student resources, you have the source files. So these source files are going to be very useful for you guys to run as you are reading the theoretical side of each one of the chapters. So make sure that you have a source file for this particular book. Okay, so you just go to the publisher's website, click on student resources, and then you download the source files. This software animations, don't really mess with that. That is applet based, and you know that most browsers do not support those applets anymore. It's just going to just give you a hard time, so don't really worry about that. We're not going to use that software. Okay.
Professor Salo,
so as far as the presentation is concerned, okay, how is the okay, so you guys not seeing it? Okay.
Yeah, we just see application sharing has stopped as soon as you start sharing it.
Really? That's not good. Okay, let me see. Yeah, that would be good if one of you would give me some feedback what you guys seeing or not. Okay. Let's start. That's not going to be good. You need to somehow share the screen. Okay, hang on guys, let me log off and then log back on and see if that's gonna help us at all. Okay, so I'm gonna be back in a couple of minutes. Okay, let's try this again. Oh, this is not good. Well, we didn't have any problems yesterday, and I've been using this for a couple of semesters, never had this issue, so I'm not really sure. Let me log off again. Okay, are you guys seeing this one? It should work right now. Can anybody click on the talk button and just give me a feedback if you guys see my screen?
Yeah, it looks fine now.
Okay, and you guys get a decent response time?
It's a little laggy, but it's viewable.
Okay, thanks. Okay, so you should be able to see Chapter 1 PowerPoint presentation. Okay. So in this particular chapter, we're going to be really talking about just basic data structures, but we're going to look at it from a different point of view, which is looking at exactly what these data structures look like and then trying to figure out some performance calculations before we start even implementing some of these algorithms. Okay? So really when we're thinking about the data side of it, we're going to be looking at the data from the processing point of view. What goes on, so not really on the input data or the output data, even though we can do some testing for that as well. And later on, if we have some time, we can look at different ways of opening files and closing files or writing files, or what happens when we read from files. Because that's going to give us a lot of different speed as well, which one has a better performance or not. But right now we're going to be looking at the processing itself internally. So because we need to look at or find places where we can store data, okay, we need to minimize that access time. So now if we are doing any kind of memory access, the memory access will require us to search for memory location available, and that's going to be much slower than if you just fetching the instructions and executing the instructions within the CPU. Now even this access mechanism also has different levels. I mean, most of you probably know that you have level 1, level 2, level 3 cache before you go to the actual physical memory, and then beside that you have the secondary storage, where you have swap space, where you're swapping memory out to the hard drive, and that's going to be the slowest one. But we're not going to really considering those kind of different memory accesses. It's either going to be just accessing memory, which is going to be slower than accessing, let's say, the CPU. Okay, so that's why we need to create an algorithm that's going to be optimized not just for organization, but the organization going to give us some more efficiency, and that's what we're going for in this course. Okay. So every time when we're talking about, different algorithms, we also need to look at the trade-off for different algorithms. So some algorithms are going to be good to access data. Some of them are going to be better to search for data. And we need to look at eventually all of these different methods. How do we structure the data, and then how do we access the data? Okay. So also one of the aspects of implementing the algorithm is the cost, right? So if you going into quantum mechanics type of things, and you're gonna be looking at algorithms that are really hard to implement, you might not go with that implementation because it just costs too much. Okay. So we also need to look at the cost, which is the programmers, right, and how much money you're gonna get out of the software. So you don't want to spend $100,000 on something that you know that you're not gonna make more than $10,000 out of it. So you need to look at the cost as well. Okay. And then eventually we come up with the matrix, and then you look at that the gray areas are basically in this table. It shows that what is acceptable and what is not acceptable. And out of all the good and bad mechanisms, then you can select the one that works best for your application. So, so we need to look at this analysis. Okay. So what we're going to be looking at speed analysis, memory overhead analysis, and then cost analysis. Okay. And those are going to be basically what we're going to call them the burden cost. Okay. And some of the terminologies, so you need to make sure that you understand some of these terminologies, the different kind of access modes, the extraction and encapsulation are the new terms in this particular chapter. And the concept of field, node, key field, and the data sets, right? So the main idea here that with the fields, okay, the fields are the smallest unit. So each field, you can have multiple fields in a node. Now, one of the fields can be designated as a key field. So those of you that took or understand databases, you kind of have the concept of these key fields. And we're talking about nodes, and in databases, those would be called like records. Right? And within the field, within the node, we have fields. Now, if the fields are different, like you have the age is an integer, and then your name is a string, those are non-homogeneous, right? They're not the same length for each one of the fields. But if the fields within the node are exactly the same data type, like in, you have the arrays, right? So so far in previous classes, especially in like C++, we learned that arrays have to be the same data type. So that means they are homogeneous data sets. So you need to understand these basic concepts, okay? And then when we have operation access modes, we have the key field and the node number based accesses. So in the key field mode, you are looking at the key field. So that means you are looking inside the node, and you're reading the information about that node, reading the field, the key field within the node, in order to determine if that is your node or not, versus the node number mode, which is going to be much faster because we don't care about what's inside the node. What you're looking at is the identifier, right? So think about it like an index value, right? I need the third node. I don't care what's in it, just give me the third one. Beside that, if you would do the key field mode, then you would have to look into the field, read the value of the field, compare it to some other value, and make a decision if that is the node that you need or not. Okay. So for basic fundamental operations, we're looking at insertion, fetching, deletion, and an update. Okay. So that's going to be the basic 4 operations that we're going to be focusing on. How does that actually work? Now, when it comes to abstractions, sometimes we really want to know how things work, especially those in engineering field or STEM fields. We always want to know how things work. Basically, in abstraction, if we have good documentation, and if we follow what we learned in C++, the self-documenting identifiers, okay? If we understand how to use, let's say, a method, how to use a data type, we don't really have to know exactly how it works inside. We just need to know its advantages or maybe disadvantages. So the abstraction is that you don't need to know exactly how it works. Okay. So that's why it's going to be very important that we also going to have good documentation in our code. So we don't need to give out the source code in order to use a method. And I think Java is really good in that because of its documentation. Java, Python, those are really good languages. Okay, so encapsulation, many times, especially those coming from C++ or just took C++ class, we hate the function calls and the whole concept of sending a variable, sending an identifier, or looking at the parameters of a function, or in Java it's called a method, and looking at it from a reference point of view versus the value point of view. And many times I see that if something doesn't work out or the function call doesn't make sense, you just make the variable global, so then all the functions can have access to it. Okay. Now that's not a good programming practice, right? So in encapsulation, everything that everything that node needs, everything that object needs to be encapsulated inside that object. And if we need to have access to some of the encapsulated fields, then we can use the abstraction layer by giving methods that has access to the actual fields. And as far as methods are concerned, right, we use a verb plus noun combination. So if we only reading some values, right, and that's one thing we learned in COSC2437, that we need to separate the methods by their function. So if you only need to read some values, read a field from an object, you use the get verb and maybe get name, right? So that implies that you're only reading something. So we call those accessors. We're only accessing the field. We are not modifying it. Now, if you want to modify something, then you use the keyword set. And with that, it's going to be, let's say, set color. With set color, you're modifying the field value. In that case, you're using a what we call a modifier, or we also call those the mutators. So then the mutators are the ones that make modifications. So if you need to read some value and then you have to modify some value, You have to have two methods. One which will read it, that will start with get, and then one with a name that starts with set to mutate the value. So keep them separate. Okay. Because we try to reduce the cost of software and software development, and we want to increase the production with the software. So that's why we're going through in these courses with these conventions. These are really not standards what we're going through. It's a good programming practice. Okay, so identifier naming standards. So with identifiers, we use the camel casing. So camel casing, we start with a lowercase letter with identifiers. With classes, we use the Pascal casing. So classes start with a capital letter. And then we have the constant values, or in Java it's called the final values. Those all capitalized. Okay? So that just makes it easier on us when we using a language or reading somebody else's code. So also think about the cost, and not just getting it done, but getting it done right. And that's going to be our focus in this particular course. Okay. So we need to look at the speed complexity and then the space complexity. So we need to look at how long an execution takes, and then how much space does it need. So if you have a really good algorithm that runs really fast, but it takes a lot of space, that's really not what we call a good algorithm, right? So you need to optimize the speed and the space complexity for your algorithm to select the right one. So with the speed complexity, we need to approximate the big O and give a big O analysis for each one of those algorithms. And that's why we need to really look at either a relative speed analysis or absolute speed analysis. And that's going to be you're going to see that there's not much difference between the two, so sometimes relative speed is much easier than absolute speed analysis, but the main thing is with relative speed analysis, you always, or the best way to start is with your pseudocode. Okay, so let's take a look at some of these things. Okay, where are we? Okay. So let's see if we have, okay, let's do relative, okay, relative speed. If we have an algorithm, okay, where you look at the algorithm, it comes up to, let's say, 300 plus 20 log 2 n, and then we have another one, let's say b is 20n plus n cubed, and then we have another one, let's say c is 5n squared plus n log n. Okay, so you have three choices. Now you'll see what this means a little bit later on when we're actually looking at the code itself. But when you have these three different codes that you're looking at, which one would you pick? Which one would you say is going to be the best one or the fastest algorithm? So one thing that we need to look at is which term grows the fastest. Okay, So first of all, when it comes to constants, we kind of ignore those. Okay, so 300, we ignore those. When we're talking about constant multipliers or dividers, we can ignore those as well. Okay, so we just get rid of those. So here we're talking about 20, we get rid of 20, and then we get rid of the multipliers right here. Now those are constant multipliers, so we get rid of those. And after that, what we end up with, in this particular case, with the first algorithm, we come up with log n. And we can't really simplify it any further. Now here in this, the second case, okay, we have n, and then we have n cubed. Now one thing you need to notice, that these are not dependent on each other, right? So these are independent from each other. That's why we use the plus sign in between, okay? So which one grows faster? Well, eventually what you're going to see is when you see something like n is going to be a loop, okay? So think about that like a for loop. So what happens if I have n value of 10? Then the for loop iterates 10 times. If I have an n value of 100, the for loop iterates 100 times. Right? Now if you have an exponent on the n, what does that mean to us? To us it means, let's say, a for loop nested inside the for loop and nested inside another for loop. Okay? Okay, this should be 3 separate for loops. Okay? Now what does that mean? The outer for loop executes n times, the inner for loop executes n times, and then the most inner for loop executes n times. So that means, where should I write it? Okay, here. N times, n times, n times, right? So these are all multiplying. That's why we have that n cubed. So think about it like a clock, right? So in a clock, you have the seconds, you have the minute hand, and you have the hour hand, right? So every time you have the time is the seconds go from 0 to 59, right? So if you have this elapsed time of per seconds, so you went and spent 60 seconds, 60 seconds is 1 minute, right? And then you go one more 60 seconds, and then it's 2 minutes. So now you have 2 times 60 seconds. So if the loops are nested, that means that you have multiples of each one of the loops, so that you multiply them. So you can see that if n is, let's say, 10, right? So let's say for the n term, how many times the n will iterate in a loop, in a for loop? 10 times, right? But now what about the n cubed? N cubed gonna mean 3 times nested loops. So that means 10 times 10 times 10. So it's going to be 1,000 times, right? So that means n cubed is taking a lot longer than n. So because of that, we get rid of n, and we only keep the slowest performing component of this equation. Okay. So let's look at this. This one is n squared. Okay. So so here we have n squared, and then we have n times log of n. Now what does that mean? Again, these are independent. So it's either going to be a nested loop, so it's going to be a for loop. Right. So we have a for loop. And then we have inside, we have another for loop. Okay. Now here, when we're talking about n times log of n, Okay, we're going to have a for loop, and inside a for loop, we're going to have the log. Well, I'll talk to you about what that log is. Okay. Think about log as every time you do something, you split that in half. Okay. So because we can split it in half, we're going to have less and less data to work with. Right. So if you need to, we're going to talk about the binary search. Okay. So what is a binary search? You start in the middle of the array. Okay, so let's say we're going to have an array. And within that array, we are looking for a particular value. Right? Let's say I'm looking for 4. Okay. So first of all, we have 7 elements. But we're going to start in the middle, and then we look at where is the element within the whole array. Well, here we're going to have a sorted array and all those kind of information. So we're going to go a little bit deeper into that. Right now, just understand that you have a set of values, and then you split that set of values into half. And at that point, you're looking only in this half, ignoring the other half. So you started for a whole set of arrays, now you only have half of the array. And after that, you're splitting that in half in order to figure out if you located the value or not. So if you keep reducing the data set that you are working with, if you are reducing the data set as you're progressing, that's going to be on logarithmic changes. Okay, so we have a for loop in this case, and then inside the for loop that's controlled by n, inside the for loop we have a logarithmically changing for loop. So that is smaller. It's getting smaller. Okay, so this is going to be a smaller component in this this particular example, this TC, because the nested for loops going to be n times n squared. So in this case, we're going to get rid of the n log of n. So because log works really efficiently, because as we are progressing through data, if we are progressing through data and we keep reducing the data set, that means log of n going to be the fastest one. So we ended up with log of n cubed, and then n squared. So which one would you choose, TA, TB, or TC? All right. So here you should choose TA, because that's going to be the fastest algorithm. So that's what you need to really focus on. If you really haven't looked at code from this point of view, this is going to be the section that you really need to focus most of your time on. Okay. So when we're looking at the absolute speed, with the absolute speed, we really need to look at the actual speed, which is the sum of different type of accesses. So we have I equals 1, and then we go to G. G is the grouping of different instructions, or basically we're going to have different times. So if we have to access the memory, that's going to have a time associated with that. So every memory access instructions going to be in the memory access group, and then any CPU access instruction is going to be in the CPU access group. So how many groups we're talking about, right? So this group, if we have, let's say, memory, and then we have just the CPU, right? But really when we're talking about memory, we have level 1, level 2, level 3 cache, and then maybe you're going to say storage. Okay. So you need to write a file to the hard drive. Okay. So here we really have 1, 2, 3, 4, 5 different groups that we need to consider. So in most of our cases, when you're talking about the group, we're only going to have two separate groups. Okay, so this is the group itself is comprised of the time and the number of instructions for that particular group. Okay, so we have the time and the number of instructions for that group. So this is where your book gives you some example to help you understand this concept. Okay, so we're going to have a non-access. Let's say, what is a non-access? Let's say a T and a non-access. That can be mathematical operations or logic. When you have an if statement or you have a while loop and you need to figure out if you have what is the Boolean result of that logic, that's a non-access. So you don't have to access the memory for that. The CPU can do it. So those kind of concepts. And let's say, what is your CPU? So we have, let's say, CPU is 2 gigahertz. Right? So that means, now this is one core, one single core. So what happens in one single core? Each core is executing one instruction at a time, right? So this is what we assume right now, that we have a core, a CPU, that executes an instruction. So that means, in our case, is one instruction. How fast? 2 times 10 to the 9. Okay. So that's gonna be 0.5 10 to the negative 9, right? Which is the same thing as 5 times 10 to the negative 8. Oops, that's 10, right? Okay. So that's how long, and this is in seconds, so that's how long it will take for one instructions to execute on this particular CPU, right? Now, what would happen if you would have 8 cores, right? Then you would have 8 instructions at any given time, right? So it's going to be much better execution time. So it depends on the CPU, and we need to understand what happens within the CPU, right? But per core, per CPU, we only have one instruction set per CPU. So what about the actual access? Okay. The actual access is how long does it take for data to be located in memory. So this is where you have, when you buy your memory that you put into your computer, you're always looking at the fastest memory. So you can have a cheap memory that's going to have a slower access time versus you have a faster memory that's going to be a little bit more expensive, right? So you need to look at how fast the memory is. So in this particular case, let's say it's 50 nanosecond chip. Okay. Now 50 nanosecond is 50 times 10 to the 9th. Okay. Oops, nanoseconds, so there's going to be negative number, which is going to be the same thing as 5 times 10 to the negative 8, right? So you can see it when we are subtracting the two, or comparing the two, right? The CPU is 100 times faster than the actual memory access. So what does that mean? That means you have to have a non-access based, or your goal is to have an algorithm or a code that's going to be non-access based. And if you do have an access based, like memory access based code, then that application will run faster, slower. Now, if you would have another variable in here, let's say storage, right? And then you would find out that storage or secondary storage devices are so slow that if you want to avoid using them. Now that's going to be improved with the storage if you're talking about solid state drives, right? So in that case, the access time improves. Now I have to add that there are different solid state drives as well. There are the cheap ones with very slow access time and the faster ones. So if you have a solid state drive and you want to test it for read-write speed, you can see that solid state drives can read really fast, much faster than your hard drive. But the writing speed is about the same speed as your hard drive, mechanics-based hard drive. So some of the cheap solid-state drives, if you have an application that's very write-intensive, like databases, right? Solid-state drive not going to give you much improvement at all. But if you need to read, solid-state drive is going to give you a much better performance. Okay, so that's going to be very important to understand this kind of a concept. Now, beside this, let's look at also the density and memory overhead. Right? This is the other thing that most of you do not consider when you are in basic courses or you are in your intro-level courses. And that's what we see when somebody says, go ahead and write a program, and you have to get the response from a user. Okay, so what happens when you get a response from a user? Right? So you're going to be basically getting information, reading information, let's say, into a string. Okay. So what happens if you read into a string? Okay. String, by default, gives you a default size of the string, and depending on the language that you have, okay, it can be anywhere from 10 to 16 characters, because you know that string is a character array, right? But if you just want to get the response from a user, then the response is, let's say, yes or no. Now, in this particular case, if this is C++, and with C++, you get a 16 characters for each string. While in C++, you're also going to have the terminating character, the /0 at the end, right? So you're really using 2 characters to store this particular response from the user. But what about all these other spaces that allocated for the string and you're not using it? Right? So if this is 16 space, then basically you're using 2 and you're wasting 14 bytes because you chose to read it into a string. Now in Java is Unicode based, so because each character takes up 2 bytes, if you storing a string and you really only need one single character for that string, okay, that one single character will take up 2 bytes. If your default value for a string is 10 character locations, then you are wasting basically 9 times 2 or 20 bytes of space. So that's very inefficient use of the data type, right? It is very inefficient use of the memory because you have so much overhead that you could use for something else. So in this particular case, what would be the right solution, right, is to use a character. And with a character, we have 1 byte, or in the case of Java, we might have 2 bytes. And that's where you are storing, let's say, the response from the user. So in this case, the primitive data type, just enough to fit the response, is a lot more efficient than going with a string, because the string gives you a lot more overhead that you are just basically wasting. So in this case, the density is information bytes. So I'm just going to say B of I, right? Information byte divided by the total bytes. Now, what is the total byte? So the information byte, which I need to store, I need it for my program, and the total byte is the actual information or storage. Okay, the information, the same thing as in the numerator, plus the bytes for the overhead, right? So in this case, right, if we have, let's say, 100 million nodes, right, and each information needs, let's say, 50 bytes. Okay, so that's going to be 50 times the 100 million, right? And that's divided by the, let's say, 50 bytes times the 100 million. But each one of the nodes that we are storing will have 10 bytes of overhead. So that's going to be 10 bytes, 10 times 10 to the 8. Okay, so that's going to be basically 0.08 or 0.83 as for the density of this application going to be. So it would be much better to get it closer to 1, right? So closer you get it to 1, better it is. So what does that mean? That means if we could get rid of the overhead, that means you need a character, you store it in the character, so that means there is no overhead. Then it's much better than if you need a character and you store it into a string. And with the string, you have maybe 14 bytes that you are wasting because you're really not using it for the response. So the density is very important. In this case, is not the speed. This is just the overhead for the density of your application. And for that, we need to know the data sizes, the data type sizes, right? So an integer is 4 bytes. So if I need 3 integers, it's going to take up 12 bytes. Now the 12 bytes is going to be much better used if you put it into a integer array than if we are using the 3 separate integer identifiers. So why would that be the case? Well, because each individual identifier will need to have a pointer, a reference variable pointing to it. So because of that reference variables, so if we have an array of integers, and we have 1, 2, 3, what does that need? That needs, let's say this is going to be the numbers, right? So the numbers is going to be a variable, The numbers variable is a reference to this array of three integers. So what is my overhead? My overhead is number, because number is an identifier. The identifier is a named memory location. Okay, so it's going to store the beginning of this array, and that's going to be our overhead. Now, if we have x equals 1, y equals 2, z equals 3, these still going to be just 4 bytes. 4 bytes for each one of these values, but then each one of them will need a separate reference pointer pointing to that location. So you can see in this case the overhead is much larger with individual variables than if we have one reference pointing to 3 consecutive values. And access time going to be much better because they're going to be, this is consecutive, right? Then we have x, y, and z separately. They're not necessarily going to be consecutive, so the access time going to be much larger because you have to find the particular memory location. Okay, so that's pretty much what this chapter is all about, right? And then it's talking about, you know, generic classes. Okay, so this is where you really need to start looking at your IDE. Okay, and then in this case, let's just create. You know, we can create a project. Okay, computer science. I'm just using BlueJ right now. So if I say, let's say chapter 1, okay, and here you just really looking at the source code that comes with the book, comes with the chapter, and then you're trying to see all these different relationships within the chapter and the code that you used to writing. So I'm just going to call it Ch01. Okay, just create a basic class. Okay. So here, so we can just create a basic class, okay, just to practice our coding, okay, or practice the debugger that we have. So let's say we're going to have a character array 1, and I don't know, let's set some characters in there. So A, B, and C. Let me see, did somebody? Oh, thanks for letting me know. Okay, can you guys see this one now? Okay, so I just started a project, a simple project. I just call it chapter 1. Okay, so make sure that the class starts with a capital letter, and it's just a simple application. So we have, let's say, character array 1, and character array 1 is going to have 3 separate characters in it. Now let's create a a string array. Let's call it 2, and let's assign ABC to that. And this is going to be automatic boxing, okay, and automatic unboxing. So if you don't feel too comfortable with Java yet, then you always need to create it by calling the constructor, okay? And that way it's going to be hopefully more obvious what you're doing. Okay, so now we have a character array that's going to have A, B, and C in it, versus we have a string array, a string, a single string, that's going to have a contents of A, B, C in it. Okay, so I just need to add another line to this just so I can actually pause or set a breakpoint. Okay, so in BlueJ you have to have a line of code in order to set a breakpoint. So I just put in this dummy line so I can put the breakpoint there. Okay, so at this point, make sure in your IDE, whatever IDE you use, set a breakpoint and then execute the code. Okay. What did I forget? It's supposed to be an array. Okay. Okay, so as you're running the code, now you can see there is the variable, the identifier 1, and the identifier 2. Okay. So now in your debugger, you can look at it and see what is the difference between the two. So there is 1. When you look at 1, what's inside of it? It has the length of 3, and then we have A, B, and C. There's nothing else there, right? Now what if we look at the string? You can see that the string encapsulates a character array. But now it has a private field, the private int hash, and the private int hash 32. So that's going to be 2 extra integers. So what does that mean? 8 extra bytes. So now we have 8 bytes, and when we look at the actual character array, the character array is exactly the same, but now the string encapsulates this character array and adds more overhead to it. So in this case, if you really just want to use A, B, and C, and you don't want to have any special type of methods that's already available with string, right? You don't want to manipulate these characters at all. You don't want to use a method to manipulate these characters, then you don't want to use the string. You want to use the character array because it gives you less overhead, right? So because it's going to be less overhead, the code going to be much more dense. And that's what you need to look at. The same kind of a data types what we talked about in previous courses, but now you are look at it at much greater detail. Okay. So now what we can also do is we can also create another string. Oops. Okay. Let's say there's going to be 3. Okay. And what if we create a new string, and we're going to send this new string 1. Okay. So what we're doing is basically we're creating this character array, and for some reason later on in the code you decide that you do want the capability of string, and then you can create this particular variable, right? And then we compile it. And then we run it again. Okay. And now we have the string variable 3, and now we added that string overhead to the same character array. Right? So you can see that just because you're using a character array, and then you might decide later on that you need a string, right? You can convert it, but if you don't need that overhead of the string, then don't use it, because your code is going to be much more efficient. Okay. So also just the concept of pointers. That's another concept that a lot of students do not understand, right? So let's say string 4. Okay, and well, we can even make it a array. So it's going to be a string array. And then what happens if we say 4 equals new string, and the string going to be, let's say we're going to have 3 strings, right? Okay. Now at this point, do we have an actual string? Did we create 3 strings? Well, if we don't know, right, make sure that you put in your breakpoint, and with the breakpoint we can launch our application, and we look at 4. 4 is a string array. You double click on that, you can see that it has 3 elements, but all 3 of those elements pointing nowhere. Okay. So just because we said string index 3, it did not create string objects, right? Because we did not instantiate the objects yet. Okay. So how do we instantiate each one of the objects? So now we can say 4, let's say index 0, and then we're gonna create a new string. Okay. And let's just create one. Hello world. Okay. So compile it, and let's see what happens now. Right. So in this case, we look at the object again. There's 4. 4 is a reference object. Okay, so that is not the object, it's just a reference object. You click on that, now you can see it has 3 elements, and by default we had null values for each one of the elements, but now it has a value. So index 0 is also a reference variable to the actual object. So then, when you click on that, now you can see this is the individual string object with the overhead, and then finally the actual character array. Okay, so make sure that you understand this concept of reference variables. Reference variables are not objects; they're just pointing to an object. Okay. And of course, this is not how we want to use this this particular assignment. So what we usually do, we're going to create a loop, right? So int equals 0, and I is less than 3, and I plus plus. So now with that, we can fill up the array locations at I, and maybe we want to add the I to our string before we actually instantiate it, right? So in this case, we're going to have all the array elements initialized to a string. Okay? So again, we look at it. We run it. Okay. String 4 is an object reference. You click on that, and you can see that you have 1, 2, and 3 strings. Okay. Now you have 3 string objects. Okay. So this line of code just created the placeholders for the reference variables, but it did not create objects. Okay. This is where we actually initialize the values. Now what happens, let's put this into a block. Okay. And let's say we're also going to have internally, we're going to have another block. And let's say j equals 0, and then j less than 3, j plus plus. Okay. And the only thing we're going to do inside here, let's create a variable. Let's say int count equals 0. And the only thing we're going to do is we're just going to increment that count inside. Right? And maybe we can give it a little more values, right? So what's going to happen here? How many times we're going to execute count? Okay. We can also print it out. If 2 the number of iterations. But what do you notice here? This is a for loop, right? And inside the for loop there is another for loop. Okay. So how many times will count execute? Well, remember it's a nested for loop, so it's going to be n times n, right? So we can also make that more clear. So we can do final int let's say size equals 4, right? So now it's much better. Right? We try to avoid magic values as much as possible, and if we need to, you need to use constants. Now, why would you use this? Because now if we need a larger or smaller array, we can change the size of it much easier. So right now, how many times will count execute? We look at the loop, how many times that loop executes. It's going to execute 4 times, and then you have an inner loop, that's another 4 times. So theoretically, that should be n times n, right? So it should be 4 times 4. So let's see if we can do this. I'm just going to add another dummy line. Right here. And then we're going to launch this code. So you can see it took actually 16 times. Okay. So because we have the 16 iteration, that's why when you're talking about big O analysis, always think about the structure of your code. And the structure of the code is going to be much easier identified if you have a flowchart or pseudocode in order to estimate your big O, the big O values. Okay. So now if it's going to go, we're going to change this to, let's say, 6. All right. Okay, and now it executes 36 times. Okay, so that's going to be the very crucial point at this point of your course, that you understand that inner loops are related to each other, so we need to multiply them. Okay, now if this loop would be separate, right, not an inner loop. Okay. Let me see. Anybody has a question? Okay, I'm not sure what that yes is, Janet. But anyway. So now if the 2 loops Now they are separate, right? So that means this loop gonna execute n times, and this loop gonna execute n times. So that's gonna be 4 times and then 4 times. So that's gonna be 4 plus 4. So that means 8 times. Okay. So in that case, it is going to be 2n and not n squared. Okay. So that's basically what you should be looking at. Not really high-level syntax or really complicated terms at this point, but if you haven't looked at your code from that point of view, especially the loops, how the loops are used in your code, and what are the data types that you use, and how much of an overhead you are putting into your code because maybe you are using the wrong data type or wrong classes for your application. Okay, then you need to look at it from that point of view. In this particular chapter, use your debugger in order to test them. Okay, so the other thing that you can do in this particular chapter is I would recommend that you import all the source code. Right? So make sure you do have the source code. So computer science, and put a source code in a meaningful place and import it into your code. Okay, and then with this code, now you can experiment with these codes. So make sure that you look at them and look at the generic applications, especially if you haven't played a lot around the generic applications. Make sure that you do that. Okay, so let me save these. So what you should do with the chapter 1 source files, okay, is you should create one of these codes, right? So this is the UML for your code that was given to you, but you do not have a driver for your code. So you can just simply write a really simple code, right? Call the weight loss class and basically call the constructor for the weight loss class. Because you're calling the weight loss class constructor, in this case the generic demo, right? Weight loss class is used by generic demo. So generic demo is using weight loss class. So that's why you have a dotted line and the arrow. Now when you look at the weight loss class, what do you notice? Here what you're doing is you're creating objects. When you create objects of person generic, right, with the generic constructor, when you look at the actual generic constructor, you can see in this particular case, because A1 is an integer and W1 is a double, T becomes an integer and E becomes a double. Okay, so private age gonna be an integer, and then weight gonna be a double value. Okay, so the T and the E is a placeholder for reference variables. Okay, remember, not primitives, but reference variables. A reference gonna be substituted into the under the values of T and E. Okay, so you can make sure that you write this code, compile it, make sure it runs, and that's how you practice the generic classes. Okay, and then you can do another one, right? With the same source code, you can have the weight loss demo, right? And in this case, you can link the weight loss class revised by calling the weight loss class revised constructor. And in that constructor, now we are calling or creating objects of weight loss client. So weight loss demo is using weight loss class revised, and weight loss class revised using weight loss client. Now the weight loss client, this code right here, okay, extends a person. So now you're also practicing inheritance, right? So coming from COSC2437, most people have a hard time understanding inheritance. So this example that comes with the chapter is really good way of reviewing that knowledge that you gained in 1437, right? So we are extending person, and by extending person, we can call the super constructor. Now the super constructor will receive A and W, and A is an integer, and then we have a W. So the UML for that is the open, wide, triangle, and solid line pointing back to the parent. Okay, so that is a good practice that you can do with the source code. So then you can change this, and you can rewrite that and make sure that you implement this flow chart, okay, or this UML diagram. And this way you can practice the generic classes. So again, you have the weight loss demo. The weight loss demo is creating an object of weight loss class revised. So weight loss demo is using the weight loss class revised. The weight loss class revised is calling the weight loss client with 3 parameters. Now when you look at the weight loss client needs to extend the person generic. Now because you are extending a generic class, the generic class data types also have to flow in to the weight loss client. So you have to change the signature, okay, from previous code. Let me see if I can bring both of them up. Okay. See how the weight loss client extends person, and there is no generic syntax after that at all. Now because you are using a generic class, you have to add that. So in order for the weight loss client to actually send the information to the person generic to its parent, you need to make sure that the weight loss client is also specifies the T and E, or the placeholders. So at this point, when you are calling the constructor for weight loss client, you are calling the constructor with T and E, and A becomes T, E becomes W, A and W is sent to the constructor. Now the constructor will receive T and E through the class definition, the class signature, and then it actually flows into the class through to the constructor. So T and E becomes integer and double, right? And that's how generics work. So so this code that you get with the compiler, right? This code is not an application. It does not have the main. It does not have a class with a main method in it. So you need to create that, and you can really create it really fast, just a few lines of code. Okay. And if you guys need help with that, right, then you guys can watch this recording. Hopefully everything was recorded, and you guys can just copy this code. But I'm not giving you the code because you guys need to type that in. Okay, that's how you learn a lot more if you are doing it yourself. Okay, but that's pretty much it. So that's pretty much chapter 1. You do have to have some kind of way of establishing at this point how you're going to get through each one of the chapters. And you can see that all this is very well explained in the book, right? The exercises are very good to help you learn the concepts. Do the review quizzes, because those are going to have also some calculations with it, so you can practice the calculations. But when it comes to really programming and understanding programming, you do have to run the code for each chapter within your IDE and use the debugger to see exactly the data structures that you're looking at. And that way, hopefully, it's going to be much easier for you guys to see the overhead and maybe the bad decisions that you made in previous courses by just looking at data types as, well, if it's a data type, I just pick one, whatever the easiest. And right now, you should be looking at not just the what we call the penmanship, if the code compiles or not, but it really be looking at things like, is it optimized? Did you pick the right data type? How much of an overhead you have because you picked the wrong data type? And how does your application performs when you're talking about 10,000, 100,000, 100 million nodes, when you have to create that many? Can your application still perform at an acceptable level? Because that's going to be another, there's another example in your book on people really don't like to wait, right? So at the very beginning of the chapter 1, it says that if you have a memory access of 100 nanoseconds, and you have, let's say, 10 memory accesses that you have to perform, and you have 400 million, or you're looking for the 400 millionth node. So with each memory access of 100 nanoseconds, right, then your access time, right, and make sure that you work all of these out, right? So 400 million, so this is the record that you're looking for, and you have 100 times 10 to the negative 9 access time, then that's going to give you 40,000 times 10 to the negative third, right, which is 40 seconds. Okay, so that means in order to locate the 400 millionth record, it will take 40 seconds. Now, look, just kind of imagine, like with Google, right? If you type in a keyword and then you press enter, if you would have to wait 40 seconds for the reply to come back, would you ever use Google? And by research, people do not like to wait more than 2 seconds. Okay, so people are not going to use your application if we do not understand data structures and we cannot calculate or pick a algorithm that performs to the expectation of the user. Okay, so this is a really good example to show that today we have a lot of data, and as the data grows, we still have to come up with new ways of handling that data within an acceptable time. So we need to look at efficiency of the algorithm, not just getting it done like we did in the previous intro courses. Okay. Yes, I equals 0 is an actual constant, right? When we do any type of comparison, that's a constant value, and then adding the value or incrementing I, that's going to be another separate access time. But I equals 0 only happens once, but I less than size is going to happen size time, and I plus plus also going to happen size time. So let me show you another one of this calculation. Okay, so here's one of the calculations in the book, in the chapter. Okay, so when you have rho equals 1 and t equals rho equals 0, t equals 0, those only going to happen once. And then you look at while, that first outer while going to happen n times. And then you have column equals 0, that's going to happen n times. And also this rho equals rho plus 1 is a separate statement outside the inner while loop, so that's also going to happen n times. Okay, so that's where something like 2 plus, right, the 2 static or 2 one-time assignment, and those one-time assignment going to have just constant value. And then we have n times n times n times, so that's going to be 3n. And then we're going to have the while loop, that the column less than n is n times n because it is internal, so it's a nested loop. Now the t equals t plus data row and column, and that's going to be a memory access. So that's going to be a little bit more taxing to your program because now you have to go to an array. But that's going to be executing n times n, and then we're going to have the column equals column plus 1, which is an update. That's also n times n, right? So that's going to be 3n squared, right? 3n squared, something like that, right? So that would be the algorithm. Just by looking at this particular example, okay, so this is what you would have to evaluate, and you can see that in this case, we can ignore the constant value, we can ignore the 3n, and we can ignore the 3, the multiplier for n. So in this case, if I need to evaluate this sample code, the big O notation is going to be n squared because of the nested while loops. Okay, so that's how you would look at it. So you can look at the absolute and relative calculations, and when you do the two calculations, you're going to see that the difference is not that much. So you can use the estimate either or. You're going to come up to close to the right value, either one of the estimation that you use. Okay, so that's going to be very useful. And by the way, I also gave you guys that link to the website and that's going to be very important, right? So this particular website, okay, I think is really nice visual way of looking at. So if we have x squared, or we say 3 times x squared, you see that the difference is not that much. So look at the horizontal line as the data grows. Okay, what happens to the horizontal line as we have growing data? So if this goes to 6, right, there's a little bit of change, but really overall the curve is not changing. Okay, so what about if we do log of x? Okay. Now you see this curve right here. Okay, as the data is growing, n is growing, you see how flat the curve is. Okay, and then we can add maybe x squared to that, right? So which algorithm would you use? X squared or log of x? As the data, let's say in this case, data grows to 5. Okay, what's going to happen to your x squared algorithm? Is never going to finish. It's going to feel like it's in an infinite loop. It might take 100 years to give you a result back, right? Because somewhere we're gonna hit that number 5 with this curve. It's going to be really, time-wise, it's going to be really long time. Now, if you click another algorithm that runs with the log of x, now you can see that when you get to 5, the previous algorithm just got it started, but now this algorithm is already done. Okay, so that's why I gave you this this particular graphical plotting website, so you guys can kind of see how that works. Okay, let's say what is the x time log of x. So we can add another one, and x time log of x. Okay, you see that's still going to be performing really well at number 5. But x squared, no, you don't want to use that, right? Because that is really a bad algorithm. You're never going to get the answer. So basically, getting the answer means whenever at the x coordinate, okay, the line crosses that coordinate. So here, think about the vertical bar like the time, how long it takes for something to run. So here with 5, it's not going to run very long. With x time log of x, it's going to run longer, so it's a worse algorithm than the one with the speed of log of x. But at least we're going to find the answer. With x squared, we might never find the answer. Okay, so in this case, if you need to control a nuclear reactor, right? In nuclear reactors, you might have to have milliseconds when you have to make some changes, right? Now, if you're using this algorithm, x squared, and you have to make some change when x is at 5, and it's going to take you 5 years, that's not going to be good for that particular application. So don't even start programming, because you're just going to waste your time. That algorithm is bad. Okay? So hopefully you guys can look at these it was on the desktop view again. Anyway, so this is the plot that I was talking about, right? Okay, which is the link on your Chapter 1 folder on eCampus. Okay, you just basically type in all these values on that website, and you can see the curves. So make sure that when you look at the curves, okay, you look at the curves. The horizontal is the number of data points. The vertical, you can look at it as a time. How long does it take for it to reach that point? So log of x, and you can also change the color. Okay, so red is the log of x, and then we can change x times log of x. So you can see if we have these three different algorithms, we're going to be going with the algorithm that is log of x. If that takes too much space, too much overhead, then maybe we're going to pick x times log of x. If that's not an option, we can try to implement x squared. If we know n will never go above 2, because maybe that's still going to be acceptable, but then we have to document it and make sure that we don't use it beyond that particular value. Okay, but that's how you need to think about these algorithms. Okay. Okay. Hopefully this was helpful to get you guys started and looking at the book a little bit differently. It is not the intro to Java type of course, and we're talking about data structures. So all the syntax and all the Java syntax, Java coding that you learned in the previous class, you have to be comfortable with. And now in this class we talk about this kind of a performance. So it does require you guys to think a little bit differently about the code and not just solve the first thing that comes to your mind. Okay, so I'll see you guys tomorrow at 9, and we will cover chapter 2. And if something comes up, make sure that you post your questions or comments on discussion board. Make sure that you do your chapter review quizzes multiple times for chapter 1, because we should be done with chapter 1, moving on to chapter 2, and at the same time work on the assignments. Okay? So I'll see you guys tomorrow.